Next on stage is for Nokia, Andreas Mäder. You will be talking about towards AI native mobile networks from 5G Advanced to 6G and beyond.
Yes, thanks a lot for having me, and pleasure to be here. So I'm from Nokia, and this is not about this. This presentation will not be about mobile phones. Also, of course, it is related to this. Nowadays, Nokia builds networks, and we are building basically the network infrastructure for the telecom industry. So all the operators, if you connect to a network, there's a big chance that basically some of the data is traversing to one of our equipment. And one of the visions which we have is that the next generation of mobile networks, which will be 6G, is becoming AI native. Why are we saying this? Because we recognize that AI has the potential to reinvent mobile networks. It means basically, if we look on the different components of the network, we have the radio. The radio is basically the air interface between the user equipment, between the device and the base station. The base station, you of course know and see probably sometimes with the antennas. Then it's a radio access network, it's a core network. There's a network management. All of this will be impacted by AI technologies. It means that we have data-driven networks, meaning that we have data-driven decisions, and that we have integrated AI components into the different solutions into the different components of the network. And this requires that we have an industrialized approach. And think of the scale, right? We're basically talking about 100,000 of different components in the network. We have the devices, the mobile phones. We are talking about millions of devices. And we need to have a way how to scale machine learning to this vast network. But first is, what is AI native? So we basically say AI is used from the start in the system design of the network. So it's not an on-top kind of design choice. We basically say, if we design a new generation, AI should be already considered from the very beginning. And that means basically that we need to have the enablers already thought in the system design from start. Then it's fundamental in the sense that such a network should run a substantial number of system functions, which is relying on inference for optimal operation, meaning that we don't have a few functions which using ML inference for operating, but maybe have half of it in the whole network. Then it should be foundational, meaning that we need a well-defined, standardized framework for operating machine learning in the network. So why do we need this? Because the network consists of components from different vendors which interwork with each other. And if we come back to this example here, right, this is now indeed a Nokia phone, but it's not really built by a Nokia company. And this needs to connect to base station from other vendors, being from us, being from Ericsson, being from Huawei. And this kind of interoperability needs to be ensured, and this needs standardization. And finally, it needs to be inherent, meaning that we would like to achieve that we don't have a fallback, or we don't need a fallback option for machine learning-based functions, meaning that we need to have the trust in the machine learning functionality that it works robust, explainable, and reliable. And why are we doing this? Of course, there's always some promise around this. First of all, we have recognized, as of course many here, machine learning provides an opportunity to solve complex functions more efficiently. And in some cases, it's even so that it finds solutions which you cannot find with heuristic kind of solutions, with kind of legacy algorithms, right? And that basically means you have a better performance. And that performance is very important because the spectrum, so the resources which are needed for transmission of data, is a very scarce resource. Another advantage is that you have the approach of continual learning, meaning that we have an ML model somewhere in the different components of the network, let's be it in the base station, right? And maybe something changes. Could be that there's a construction site, or maybe there is something happening in the base station itself. There's new hardware, there's a change. Then the machine learning model can be updated after some monitoring and can be played back into the base station, and the performance of the base station basically adapts to the environment. Then it will be hardware accelerated. So we are betting that in the future we have generic hardware acceleration for inference, which makes it more cost efficient compared to the specialized hardware which we have today. Then of course data-driven insights. So that's what we also have seen, right, in the different talks today and yesterday. It's always a big theme. But we go even a step further and say we want to have AI ops network automation, meaning that we want to use AI to do network automation and do do decisions in the network based on insights. So that's the promise, but what are the challenges? And it's nearly always the same. This is also what I have seen, right? It starts with the data, so how to get the data. And we have also seen with a talk from the colleague from telecom, it's actually very difficult to get the data. And now, if you think about that, basically we are talking about machine learning models in the radio, which are operating on a millisecond scale. We need to have data, which is actually obtained on a millisecond scale. And this needs to be done in an efficient manner. And this needs to be solved to make this whole operation feasible. Then scale. So there's a lot about industrializing machine learning. There's a lot about ML ops principles. This needs to be established in an efficient way. Only then it really pays off. Then we need ecosystem and standards because of interoperability issues between the different vendors. And then also trust and governance, meaning that we need to be able to trust the models such that we don't need any fallback in some cases, right? We need to understand them because in a radio network, we cannot really afford to have errors in the 10% range or even in the 5% range or something like this, because even then what will happen is basically that you as a user lose your connection and you are simply unhappy, right? And nobody wants that. So all this requires a joint effort of industry and also of academia and also of the regulators in order to put the right frameworks in place. So where are we in this journey? So towards the AI native system. So nowadays we have the 5G networks, and if you have your mobile phone, you see it with a small 5G logo right in front of it. Or even there, we already have machine learning solutions embedded, right? At least in the UE, we have it also in the base station. But there is no interoperability between these kind of components. And this means that basically it's contained in silos, so to say. We have a lot of different data formats. There's no standardization, which enables exchange of data between the different components and which do not allow end-to-end kind of solutions, right? Then we have 5G-Advanced, so that's the currently standardized technology. And there we have the first study and also the first implementation of different components. It's like a test balloon, if you want. So we'd like to understand how does it work, what are the challenges, how can we make it better, how can we improve it in the future. So we need POCs, proof of concepts, we need field deployments in order to make this happen, understand it better. And one of the key components here is this enhancements for data collection automation. And then 6G, so the first step in the AI native system, where we basically have AI integrated in all layers. We have trusted AI. And also we say we have distributed and federated AI, meaning basically that we have interaction, federated learning, transfer learning. So all these different technologies which you can leverage on if you have a full network, and you can transfer knowledge from different components to others. So if we zoom in a bit closer, you basically see here how far are we away from this. And you see here the 6G study starts in 2025, and then you can think about, it takes approximately 3 years, 4 years to complete the study and to do the standardization normative phase. And then afterwards, we will see the first implementations in the field around, I would say, 2029, 2030. And just an example, if we say AI nativeness at all layers and in all devices. So here we again have basically the different components. Just an example of where can machine learning approaches be applied. And it's basically everywhere, right? I mean, classical kind of problems like resource scheduling, meaning basically which data I put on which blocks in the scheduler for the radio transmission when. This is a hard, NP-hard problem, and this can be solved with machine learning in a much more efficient manner. So we have implementation and testings of this. Same is in the UE side and in the core network optimization, network robustness and resilience. So basically what we see here is that the applications of machine learning in the network are nearly limitless. You can put it nearly everywhere. The hard part is you have to find the right use cases. You have to make the right decisions which drive the most gain, right? But that's always, I think, in application of a new technology like this. If we now zoom a bit into the physical layer, so the physical layer is basically the transmission layer on the radio, which is really responsible for sending the bits and bit level and the symbol level between the device and between the base station. And you see here that the classical approach here, right? We have this kind of classical architecture where we have the encoding, symbol mapping, modulation, waveform, and so on. You see it's basically different blocks which are processed after each other, right? And then in the 5G advanced phase first, we say in first phase we say, okay, we look on this different kind of components and replace some of those as machine learning components and see is it better or is it not better? Does it work better? And we will later see in most cases it works better. And in the second step, we can say, hey, why don't we combine, right? We basically have these different components like channel estimation, equalization, demapping. Let's put it into one block. Let's create one model which does all of this together and see, will it improve the performance? And you guess maybe already, yes, it does improve the performance significantly. And then in the 6G, we can even do the same on the transmitter side, and we can do the same on the receiver side. And if you really think this through to the end, you can even say you can basically learn the cross radio functionality between transmitter and receiver on your own, so to say, by the network in order to get the best performance. But this, of course, requires quite some, let's say, also standardization effort and understanding of what is really happening here. Let's zoom out a bit further and we look in the radio access network again. So we have the mobile devices and the radio network and the base stations basically. And of course we can have AI in the devices as said already, right? That's already happening today, but not in the modem. So the modem is basically the part which is responsible for the transmission of data to the network, right? So you can have AI in the devices. You can have AI in the radio. And what you will have then as an additional component is that we have joint machine learning inference. So we have basically an inference machine learning operation which is jointly done on the device side and on the network side. So in that specific example, it could be something like a variational autoencoder structure, right, where you basically use it for compression on the on the device side. And on the base station side, you use generative AI to reconstruct the signal from the devices. And all this basically requires a kind of common framework, signaling framework, life cycle management of model, what I call telecom ML ops. So it needs to be industrialized. It needs to be available in each of the base stations, also on the device side. If we zoom out a bit further, now basically we see the mobile devices, we see the radio network, and we see the core network. And you can think of it maybe core network component somewhere in Frankfurt in a data center, right? And radio network is basically in the area of whole of Germany or something like this. And the mobile devices, there are 100 million maybe active in the networks, right? And then what we say is, okay, the AI native system enables AI in all parts of the networks, interoperable and end-to-end, meaning you also have end-to-end kind of use cases where the different components can really work together and need some kind of orchestration, collaboration model in order to achieve that. You need privacy preserving data collection framework, very important. Privacy laws needs to be, of course, obeyed. And that's a difficult problem sometimes because if you move around with your mobile, you are basically more or less detectable. So a smart machine learning model can identify, okay, this is Markus Gruber because he moved out in a common pattern since every day and so on, right? And we need to find some ways how to prevent this. And there are techniques to do this, of course, also related to transfer learning or differential privacy techniques and so on, but still something which needs to be understood a bit better. Telecom MLOps, I think I said already. And then we need intent-based management orchestration, meaning that instead of doing complex kind of configurations, if you do some changes, we simply state the intent. We want to have something. We say, for example, we want to have an end-to-end slice which enables a good quality of service for video users, something like this, yeah? And the network does it on its own. So we don't need to touch anything, ideally, with manual labor. And you say, okay, these are all nice slides, right? So will this ever happen? And happy to say that yes. So we have implementation of this. You see here our lab in Espoo in Finland. You see here signal generators, right? And also have a small kind of videos, which is basically this deep RX machine learning based receiver. And if you just watch here, look on the red dots or on the red curves, basically you see here that there's a significant better performance in this channel setup compared to the legacy receiver. So there are clearly gains observable for machine learning based approaches. There's also another example here for machine learning based TSI feedback compression, but maybe I skip this. I simply say here that if we look on the whole protocol stack in the radio, and we look on where can we apply, what are the gains which we observe. The gains are there, 3 dB, 4 dB. 3 dB basically means double the performance, right? So this is a significant improvement. And this is not only in one component, this is in many components across the board. So you cannot simply add them up, but you see the gains are there. And therefore, I think it will also become a reality inevitably. So, okay, then, but what about large language model? You may ask, there's a lot of discussion about large language model. They didn't talk about this at all, right? But of course, it also has a place. On the one side, we have, of course, the same kind of challenges or use cases which every other industry also has, right? We can use large language models for summarization, insights, generation of any kind of content. So there are thousands of documents about some internal specifications which can be understood. There are standardization documents. So we will build something which we call telecom LLMs, which are specialized for this specific kind of language, right? But there's even something more interesting from my point of view. We can also use LLMs to create networks. And there's a concept like network as code, right, which basically means that the network configuration is closely tied to the application level, which allows a better monetization of the network. The LLMs will be instrumental in making this efficient and coming back to this kind of intent-based management. In this case, it could even be called something like intent-based network creation. You say you want this network, and the LLM basically creates the code for you and isn't deployed into the network, rolled out, and then becomes operational, which is here you see in this green slice basically. And coming to an end. So first of all, AI/ML in 5G-Advanced, so that's basically more or less the current generation, is a foundation for AI native 6G. So AI native 6G, maybe 5-6 years away. It's a journey of the whole industry. So it's not something one vendor can do alone or one operator can do alone. Simply not possible because of the scale of the challenge. And standardization is needed across the different interfaces directly in order to make this happen. Otherwise, it will not work. And yeah, coming to an end and open for your question.
Thanks a lot. Already some questions here. Yeah, please.
You mentioned something about taking LLMs to create networks. So do you mean network configuration or what do you mean by creating?
Yes, network configuration, but then it should also be automatically, if possible, deployed and instantiated if you want so, right? So
that will be created based on the factors coming from the product itself, right?
yes.
Very cool stuff. Just what do you feel about security? I mean, putting networks to
Yeah.
every base of our critical
Yeah.
infrastructure and then maybe have suppliers like Huawei or
So, yeah, good question. So,
trust the European companies.
yeah. Yeah, therefore, this regulative aspect is very important. Also, that this is clear, and this needs to be trusted also from security point of view. And maybe what's also maybe should be clear is that the idea is not to exchange models like that, right? So you don't have an ONNX model or something which you send around, but these are still proprietary in the sense that it's basically done by the vendors. Of course, I guess it needs to be done. It needs to be aligned with the regulatory, like in Germany, which we have, right?
I would like to ask you about the role that RAN intelligence
The RAN intelligence, yes, okay.
especially for non-real-time applications and
Yeah.
real-time applications. My second question is that you mentioned that one of the enablers of 6G is the usage of hardware accelerator. So it means that the problem with them is that how do you tackle really compatibility? It means that if you want to use FPGAs or TPUs or ASICs, so the problem is that you have different components in the network. How do you tackle compatibility?
Yeah. Yeah, on the first question, RAN intelligent controller, if I guess audience maybe doesn't know, right? So there is basically an architecture component driven by a standardization organization called ORAN. So it's also heavily driven by network operators. And one of these innovations is basically so-called RIC, RAN intelligence controller, which can orchestrate several base stations across a certain area, I would say near real time. That's basically the number, the meaning of it. And yes, it has an important role, and it's a part of the functional architecture, I would say, of 6G from our point of view.
But where it is going to be run directly in the core network?
I think this very much depends from the deployment of the infrastructure, also of the operator, right? Could be in the edge. If the core network is, could also be in the core network, can even be in the far edge if you want so. But then the question is, does it make sense in the end?
Yeah, thank you. We are now at an end, and all further questions, feel free to ask you probably later on this day. Thank you again, and we will move on to the next presentation. Yeah.